Speaker is Fadwa Mellouhi. She's from Hamad bin Khalifa University in Qatar. And Fadwa's research focuses on accelerating the discovery of materials for decarbonizing the energy sector. She uses a combination of computational physics and chemistry and artificial intelligence. And today she's going to talk to us specifically about her work in data-driven materials discovery. So I'll hand over to you now, Fadwa.
Thank you very much. Thank you for Kenny for the invitation. So without further ado, so I'll move to the next slides. So here's the outline of my just make sure that I can, yes. So here's the outline. So I'll be telling you a little bit about recent advances in data-driven materials discovery. And, I find it insightful that the first speaker actually talked about what we do for molecules, but I am more, I'm a physicist, so I will be more talking about extended systems and, periodic systems and so on. So, and I will give you some insights and so on in terms of what we can do in terms of data, how we can actually build machine learning predictors, and what are the challenges and the opportunities as well. Okay, so just quick background. So I am indeed motivated by the desire actually to curb or to lower the carbon emissions, like by intervention, coming from of course social and economic and environmental aspects. And I mean, what interests me is really on how to have this complementary framework between renewable energy, carbon capture, utilization, natural gas, and so on and so forth. So I work on renewables, but I also work on actually in catalysis, trying actually to find more eco-friendly catalysts and so on. So just to give you a quick introduction, so I mean, this what I will be presenting is quite extensive. So you can see that, I mean, we have leveraged the power of materials informatics, electronic structural calculations, automated workflows, and as well as big data analysis and machine learning. And also, I mean, we had the chance to work towards actually validating some of our predictions in laboratory setup. And then you can see that, I mean, this materials accelerator that we worked on actually is funded by the entities listed here, actually had we had the chance to look into niche materials for light harvesting, for energy storage materials, for hydrogen production, carbon capture, and also materials degradation. You might guess that each of these actually would require different skill sets, different methods, and so on. And I will give you like some overview of like what are the challenges and opportunities, and also actually what we need to do as a community. I mean, if anyone is interested by collaborating. So very quickly, we know that AI now, I mean, is in the hands of everyone, but what is really actually the oil for that is really data sources. So what you can see here, so these are some data sources that have emerged in the community. So we had the experimental data sources from ICSD, but also, I mean, we have growth and significant growth in the availability of data. Yesterday and also tomorrow and after tomorrow, so I attended the NGI initiative, so Materials Genome Initiative. It was the very first actually that really wanted to perturb and also revolutionize the manufacturing sector using data science and the material science. And I mean, we have also actually several initiatives in Europe and US actually that have helped us to gather data. And then if I move forward, so for example, I mean, if we take the example of how we would build and validate machine learning models, okay? So we need at first actually to set our targets, right? So what are our target properties? And then, I mean, in the case of like perovskites, like the one that I will be showing you, so the way we do is that we try actually to build the databases and train early machine learning models, and then we challenge them, okay, via lab synthesis and characterization to identify the gap between ML prediction and the lab synthesis. And then, I mean, we go for another round where we try to reinforce our DFT database and train the model, taking into account the feedback from phase 2. So you might guess that for like materials like space, like the ones I study, like perovskites and so on. I mean, the size of the supercell can be really big. So I mean, in this case, so we had to go for no less than 2 by 2 by 2 supercells, which is computationally very, very demanding. But this is to get quality data. The point here is that how can I actually get decent machine learning models using different over-the-shelf methods like random forest and XGBoost and deep learning as well. I mean, without actually necessarily needing actually thousands of DFT data points. So let me tell you a little bit about the perovskite predictor, okay? So this is one of our lab-validated machine learning models for predicting the stability and the band gap of mixed cation hybrid perovskite. So why mixed cation? So just a very quick overview. So this class of materials actually is used for photovoltaics mainly, and it is intrinsically like metastable. So one of the ways that experimentalists in the lab, I mean, have found to make it stable is to mix the cation, and the cation actually is sitting in in this cavity here. Okay, so you see here, for example, so this is the scheme of work, and then if you want to introduce different mixtures of cations, okay. So let me just my slide is not going. Okay, so you see that, I mean, in this class of material, I mean, it has been studied a very long time ago. So due to the popularity of oxide, perovskite, right? So we have some metrics that we can actually calculate just from the structural properties, okay? But what is important for this class is really the amount of distortion of this octahedra. So this is the ideal case, but the more metastable the material is, the more distortion and rotation of this octahedra you will see, which means that, you can calculate, if you manage to relax the structure, you can calculate these descriptors. The problem with hybrid perovskite is that when you inject actually an organic molecule, this descriptor, like, for example, the tolerance factor. So for example, you see, so we have here like inorganics, but we have also organics, okay? That's actually, we have looked at like different classes, okay? In this case, so these are halides and oxides and so on and so forth. And then we use different ions as well. So you can see that if you are dealing with inorganics, the tolerance factor actually works perfectly, okay? But then as soon as you start to mix cations, and then because of course of the hydrogen bonding, which is involved here, then, I mean, this actually metric is no longer good, okay? And actually we learned it, I would say, the hard way. So if you look here, so there are comprehensive databases for inorganics, but very few for organic inorganic. And these are not actually enough to calculate the quantity that would tell us whether actually this material is stable against the composition to the original component. And this is actually how we started to visualize the data and so on. So these are the parameters, which are lambda and sigma, which is the octahedral elongation and the rotation in this case. So we had to come up with a new descriptor for hybrid perovskites. And whenever you come with a new descriptor, you have really to validate it. So we came up with a descriptor, and for each composition, actually, we did perform two types of calculations. A calculation where we constrain the atoms to the cubic structure, okay, and where we don't allow them to relax at all, and then another calculation where we let it fully relax. And this energy difference, which is in the enthalpy of formation of, I mean, we have been able to demonstrate that it is actually the equivalent, or it can characterize or represent the stability of these materials. So just to give you an idea, so this predictor in this case, so I've picked like one of the, you see, we don't have that much data, but actually we can get very good R-square and MSE in this case. And then you can see that, I mean, from these models, actually we can call them for this class of materials. So either oxides, selenides, the perovskites that are based on indium or bromide. And then we can actually look at their stability. So the yellow shaded area here shows the metastability area, okay, so where you would expect this material to be metastable, and this applies here as well. And then you can see that, you have the chalcogenide perovskite and halide perovskite. I have to mention something. So we tried actually to come up with generalized actually model that could work for both chalcogenides and perovskites. But when you mix two families of materials, so you have different behaviors, and then this means that the number of features that you will be considering will be increasing, and so on and so forth. So I had mentioned that we had even attempts actually to come up with models that only take into consideration the constitution or the elemental features in this case. What you can get also from this kind of predictors here, so you can get these diagrams. Okay, this is like the mixture of three cations. So we allow the mixture of up to three cations. The green dots here, they represent actually experimentally reported data. So what I want actually to emphasize in this slide is that we have been able actually to create a tool that enables us to map out the energy landscape for perovskites, and then we compared also the efficiency of delta HC, our new descriptor, compared to the tolerance factor. So the tolerance factor, if you take it as is, which is mainly dependent on the radii, okay, of your molecules in this case, when you combine them. So if you take it as is, it would wrongly predict that some of the materials are not stable. Okay, so you see here, for example, for this stoichiometry. Okay, so but what was reported experimentally by mixing, for example, cesium, methylammonium, dimethylammonium with within a cage of lead iodide, shows us that tolerance factor is not actually very good for this class of material. So what we've done is that we challenged the tolerance factor, and then we looked and we tried to take a mixture of methylammonium, cesium, dimethylammonium, and we went through this line, okay, along this line, and we synthesized all the compositions that you see along this line. So here, you are in the zone where it is rich in it is rich in cesium, and then in methylammonium, and then you have highly stable materials. However, so we had actually looked actually using so we grew the thin film. This was like a collaboration, and we looked at the quality of the grains and so on, that all characterize or give us insights on the quality of the materials. And also we looked via XRD. So this was the kind of validation that we did for the perovskite. And as I explained to you, so from that feedback we got from the experimentalists, we went back and we made the database bigger. We said, okay, maybe we need more learning, more data, okay, to be able to extrapolate and also to give more insights on the stability. So that's all what I have for the perovskite. Another class of material that I wanted to tell you about, so catalysis. So I told you that I'm trying to do to work on green energy, which means that we would like actually to find catalysts that are based on non-expensive minerals. And of course, we want to design them for oil and gas and anti-pollution application as well. Okay, so you can see here, so these are mainly surface reactions, okay, that you are interested in. However, before you start to do any surface reaction, you have also to actually look into the abundance and so on. How, in terms of how these materials can be designed. Okay, so we can look at that. But what I wanted actually to emphasize is that some of the very important DFT data, okay, that we we usually actually get from calculating the band gap and also the band edges, the valence band maximum and the conduction band minimum, is, I mean, they enable us actually to look at the potential and the alignment, okay, of sorry, each of these like compound here, okay, that you can see, okay, with actually the oxidation level and also with the water to hydrogen level and things like that. What I want to emphasize is that, I mean, very recently, the community started to store this very valuable information. So now, for example, we have the Open Catalyst database, and we have also the OC20, OC23, and so on and so forth. But I wanted to also notice that, for example, these like materials in particular, these are oxysulfide, oxyselenide, and so on and so forth, that we are actually tailoring actually to try to see their potential for this catalyst predictors. So I would say we are, as a community, we are doing well, but actually there's a lot of information in published papers, I mean, that we could pull and benefit from, but then this really needs the effort to be able to bring this catalysis data together. Another aspect I want to emphasize on is actually I talked about workflows. So in the case of perovskites, we used automated workflows, but in this case, I mean, we had to set in advance, okay, what are the compositions that we want and so on. So this is why, I mean, we had to do these like different cycles, like phase 1, phase 2, and so on and so forth. So we had no guidance and no guidance apart from our intuition, okay, of what materials would be stable or not. So what we got interested in is that we wanted actually to see whether actually we can be more sustainable when we do our calculations. Can we actually save more computer time while searching for stable materials? So what we have looked at, we looked at the utilization of Bayesian optimization. So your Bayesian optimization is largely used in, especially in self-driving labs and so on. So where you do not actually program your machine to do the entire experiments, but then you learn on the fly, okay, and based on what you analyze, you make the next decision of what would be the next batch of experiments that you would perform. The same thing in the case of computation, and of course, so we are working in high performance computing environment. So, but actually, what actually we faced ourselves is that Bayesian optimization is often used in sequential way. Okay, so you're acquiring your data in a sequential way, and this is one of the bottlenecks of BO. Okay, so what we wanted to do, so we had a quite generous supercomputer, and we wanted to see whether we could maximize the use of HPC system by enabling BO to suggest multiple candidate materials. And in this case, so DFT is actually the true the true value, okay, that we are comparing in this case. Okay, so here in this case, so this is, sorry, this is, we applied it again to this class of material that we know very well. Okay, so we wanted to explore how our challenge really push the limits for the tolerance factor and for our descriptor, and then to which extent actually we can accommodate large cations in halide perovskite, because they're known actually to stabilize this halide perovskite experimentally, but from intuition, okay, we usually stick to very, very small concentration. Okay, this was the case. Okay, this was the case, for example, for these molecules. So we looked at the conventional molecule, methylammonium, ethylammonium, and this is a fluorinated ethylammonium. Okay, why fluorinated ethylammonium? These materials, they suffer from problem of degradation in contact with water. And we had some actually work that has proved from DFT that if we involve fluorinated molecules, so we can, prevent the water degradation. The problem is that you can see, if you just compare, I mean, this is the potential energy surface. If you just compare the sizes as well, okay, so fitting actually this FEA within the cage appears to be impossible. Okay. So what we did is that, so we started actually our basin optimization search. So these are the number of bio optimization that we have done. Okay, and then surprisingly, okay, so we had the so this is on this axis. So you have the delta H, so the enthalpy of formation, which is actually estimated using DFT, but based on like bio calculations. And this one actually is the concentration. So you can see that, I mean, contrary to our like researcher intuition, so we found that, I mean, while in like exploring the compositional space. So we found that some of the compositions that can have quite high concentration of FEA in this case could be stable, okay, and contrary to what we have predicted. Now, okay, so now if you see here, okay, so this is actually the minimum actually that we have been able to find within 60 iteration in this case. What I want to say is that this actually has been possible, okay, because actually we found a way on how to actually make this like job schedules and so on and so forth in parallel. Another aspect actually that I want to highlight. So I've started talking about data and so on and so forth from the beginning, and this is the topic, right, of this talk. But what I need to really emphasize is that if you want to be mindful now for your CPU and GPU time, right, because we're trying to make sustainable materials, but our computation need to be informed and also. So I would really recommend actually that you, before you engage in any training, okay, that you analyze your data. So try to look at the box plots to identify any outliers, okay, before actually engaging into the training. Try to see the distribution of your data, whether, I mean, it's localized and also, and then most importantly, so look at your feature importance, how they correlate with each other, and also with the target value. And then I would say, after that you can move forward and then train your data. But what I wanted to bring here is that the quality of the data is very important and needs to be really taken into consideration even before we try actually by trial and error actually to get the best model, or just to, for example, increase the computational cost, while actually we can really cut significantly on GPU and CPU time actually if we do it in a responsible way. Okay, so still have some time. Something also that I want actually to emphasize. So what I've shown here is a regression problem, but sometimes, okay, you need actually to perform like clustering. Okay, and in materials science, okay, the data, okay, when you are lucky to find like good quality data, sometimes if you want to categorize them or to like form clusters and try to look at some families and things like that, we sometimes encounter problems when we have overlapping like data. This is one of the cases where we were studying metal organic framework. So we use the core MOF database, and then our objectives was really to try to like categorize them into families to be able actually to make predictions and also to build actually like further applications regarding to that. So you can see, for example, so if so we invested some time, okay, into calculating some topology descriptors, and we added chemical descriptors and also some application descriptor. When I talk about application descriptor here, in this case, this is the CO2 capture. So in this case, so it's the capacity and also the competition between water and so on, CO2 and water. So you can see if you run the principal component analysis, okay, and if you run it once, 3 times, and several times, you will see that the way it clusters it's going to be like non-consistent and so on. And sometimes, you have that data that are overlapping. So I want to just invite you. I don't have a lot of time to talk about that, but we came up with a way actually to where we combined MCLUST and LDA in this case. To be able to classify this. If we have the chance during Q&A, I would be happy to talk about that. But I wanted to raise awareness, because in the papers, we often see very colorful, nice clustering images and so on and so forth, but really they give very little information. Okay, they really do not help us to progress with the design and with the desired properties, because you're not able to deconvolute. Okay, finally, so since my colleague actually talked about interatomic potentials, so these are also extremely important, actually, if you want to look at a really large scale. So, for example, we have some interest into materials degradation applied to corrosion and batteries. Okay, and you see here is if you want actually to really have like a multi-scale scheme, so you can move from the surface roughness, cracks, and so on and so forth. There's so many phenomena that are starting at the atomistic level. Okay, so and the different levels, like the lattice defects, the 1D defects, and so on and so forth, require that we develop actually machine learning potentials that are transferable, that are able actually to handle this situations, and of course that scale well with our resources. Okay, this is just to give you some idea. This is some work we are really proud of for the following reason. So this is pure DFT calculations. Okay, this is a slab. This has been done with VASP using PBE. What else? And then, what we did here, we looked at the effect of different defect clusters, okay, and also actually what would be actually the energy, okay, needed to actually remove iron atoms and have carbon diffusing. Then once this is done, you can use this information to build some interatomic potential. For this kind of problems, reactive force fields are actually the best option, but with the emergence of machine learning potentials, I see that there is also some potential. The only issue is that we need a lot of data. And this is why I'm calling the community to work together to work towards standardized. And I know there are initiatives in Europe and somewhere else, but towards standardized, data sharing, data repositories as well. Okay. Final slide, sorry, is that I wanted to show you also the power of reactive molecular dynamics. Okay, so when you have reactions like that, okay, so this is a slab, okay, where of iron, and the gas, the environment actually has water and so on. So this is to simulate really the dusting corrosion for iron with and without water, but you can see that you can get images that have the potential. I wish we could do that, but that they have the potential actually to be compared to advanced characterization techniques and imaging techniques. Okay, in this case, so to really validate whether your hypothesis is true, whether what is happening here in terms of interdiffusion, okay, of carbon into the bulk and then iron towards the surface, validate actually the hypothesis that you have put. With this, I think, this is just in case. So just I want to tell you that, so I think that there is still room for algorithmic development for clustering of overlapping materials and the design of materials for direct air capture in this case. And also, so I would like to also advocate for the possibility of using parallel BO, okay, if it's possible, with other partners on self-driving laboratories, and if we can actually avail for the speed up that we can obtain from such techniques for the chemical synthesis of novel materials. I've put here AI lab robots. this is actually where we see that, you know, the future is of speeding up on validating, you know, this, and where we can have actually back and forth connection between the robot and also the databases and the DFT calculations or machine learning potential calculations. Why not? So within an integrated framework. And with that, so these are some selected publications. I would like to acknowledge the funders, also my collaborators from Qatar and also from over the world. And that's it. Thank you.